In this chapter, we're going to be going over empirical and theoretical probabilities. So first, starting off with a few definitions. For the definition of an experiment is a controlled operation that yields a certain set of results, and these results in the experiment are going to be called outcomes. And an event is a subcollection, so one or more of the outcomes of an experiment. Okay, so we're going to be using these terms a lot for this section. So for example, when we roll a die, so assuming it's a six-sided fair die, the event of rolling a number greater than 2 can be satisfied by any one of 4 outcomes. Those are just going to be the numbers greater than 2, which are going to be 3, 4, 5, and 6. So the two types of probability that we're going to be going over in this section are going to be empirical probability, which is also known as experimental probability, and theoretical probability, which is essentially mathematical probability. So when we're solving these problems, we have to remember that the probability of an event is always going to be a number between 0 and 1 that represents 0% to 100%, and we can obviously include the 0 and the 1 here. And we can also write these answers, these probabilities, as a decimal or a fraction. Okay, so let's start off with empirical probability. Like we just mentioned, it's also called experimental probability. So this is going to be determined based on actual observations from an experiment. And what this is going to be the relative frequency of occurrence of an event. So the relative frequency is essentially just a ratio. And this formula right here is going to be how we determine it. We read that first part as the probability of an event E. It's going to equal the number of times event E has occurred divided by the total number of times the experiment has been performed. So it's just a ratio. So for example, if we have 100 coin tosses of a fair coin, so fair coin just means it's equally likely for heads to pop up as it is for tails, both 50-50. So in 100 coin tosses of a fair coin, 44 landed heads up. Determine the empirical probability of the coin landing heads up. So let's let event E be the event that the coin lands heads up. So the empirical probability is going to be the probability of event E equals the number of times E occurred, which was 44, divided by the total number of times the experiment has been performed, 100 tosses total, so 44 out of 100. You can reduce that fraction, or you can write it as a decimal, which would be 0.44. So we tend to not use percentages as much in probability, but that would represent 44%. Okay, the next one, we have a pharmaceutical company is testing a drug that's supposed to help reduce high blood pressure. The drug is given to 500 individuals with the following outcomes. So in 379 of them, the blood pressure was reduced. 62 of them, the blood pressure was unchanged. And 59 of them, the blood pressure increased. So we want to know if this drug is given to an individual, determine the empirical probability that the person's blood pressure is reduced, unchanged, and increased. Okay, so once again, we're working with empirical probability because it's experimental. We actually have data here, we have observations. So for the first one, for A, for the empirical probability that the person's blood pressure is reduced, so that's just going to be the number of people who have their blood pressure reduced over the total number of individuals. So that's going to be 379 over 500. I'm going to write this out kind of a little bit nicer here. So let's say once again that event E is that their blood pressure is reduced. So now we can write it as the probability of event E is 379 over 500. So once again, we can write it as a decimal. You can just divide those two numbers and get 0.758. Okay, for the next one, we have the empirical probability that the blood pressure is unchanged. So this time it's going to be E is the event that the blood pressure is unchanged. So probability of E is the number of times it was unchanged in our data, which was 62, divided by, once again, the total number of individuals, which was 500. So 62 over 500, we can reduce the fraction, or we can just divide and get 0.124. Okay, last one, we want the probability for increased. So this time, E is going to be the event that the blood pressure is increased. So probability of this happening is the number of times that it happened in our data, which is 59, divided by the total number of individuals, which once again is 500. So when we divide this out, we're going to end up getting 0.118. Okay, so empirical probabilities are going to be used when theoretical probabilities cannot be calculated. So for example, something like life insurance companies, they're going to use empirical probabilities. They're going to be looking at actual past data to determine the chance of an individual in a certain profession with certain risk factors and living to a certain age. Okay, so before we get into theoretical probability, let's take a look at the law of large numbers. This is a very important concept in probability and statistics. So to do an example before we have this exact definition here, I'm sure that most of us are going to accept the fact that if we toss a fair coin many times, it's going to land heads up about half of the time. So we should probably guess that the probability that a fair coin is going to land heads up is 1/2 or 1/2. So we want to ask ourselves now, does this mean that if we toss a coin twice, will it land heads up exactly once? If a coin is tossed 10 times, is there going to be exactly 5 heads? And we can keep on going with this. And the answer is obviously no. We can obviously toss a coin 10 times and not have exactly 5 heads. So then it comes down to, what does it mean when we say that the probability that a fair coin will land heads up is 1/2? So let's take a look at this example down here. So on the left, we have the number of tosses. So just a random number of tosses. We tossed the coin 10 times, then we tossed it 100 times, and 1,000, 10,000, 100,000. And then we're going to write down in this column the expected number of heads. And then we're going to write down in this column the actual number of heads that we observed. And then we're going to do the relative frequency of heads on the right column. Okay, so for the expected number of heads, we should probably expect that there's going to be half heads. So if we toss it 10 times, we probably expect 5 heads. Okay, so let's just do this whole column because it's pretty simple. For the next thing, we toss it 100 times, so we should expect 50 heads. If we toss it 1,000 times, we expect 500 heads. We toss it 10,000 times, we expect 5,000 heads. We toss it 100,000 times, we expect 50,000 heads. Okay, so that's actually where we would get that theoretical probability that we'll be doing in a second, where we expect it to be half. So let's say we do this. Let's say we tossed a coin 10 times, and let's say we only get 4 heads. Okay, and then let's say that we can calculate the relative frequency right now. The relative frequency of heads, if we get 4 of them, is going to be 4 over the total number of flips, which is 10. So we get 0.4. Okay, and let's say we toss it 100 times and we get 45 heads. And we can calculate the relative frequency. That's 45 out of 100, which is 0.45. And let's say we toss it 1,000 times and we get 546 heads. That's going to be a relative frequency of 546 over 1,000, which is going to be 0.546. And then let's say we toss it 10,000 times and we get 4,852 heads. So relative frequency of 4,852 divided by 10,000 is going to be 0.4852. And then for the last one, we have 100,000, and let's say we get 49,770 heads. That's going to give us a relative frequency of 770 over 100,000, which is going to be 0.49770. We don't need to write the 0 at the end. Okay, so hopefully those numbers for getting the actual number of heads observed is believable. It's not exactly the same number of expected number of heads for each one. So this law of large numbers is going to tell us that the more times we do the experiment, so we are doing it more and more, 10, 100, 1,000, 10,000, 100,000, that means the relative frequency is going to approach or get closer and closer to the theoretical or actual probability of the event happening. So you can see the more times that we flipped it, the relative frequency is getting closer and closer to 0.5, which would be our 50% or our 1/2. So here's another way of putting that definition is the law of large numbers states that probability statements apply to a large number of trials, not to a single trial. It's the relative frequency over a long period of time, which essentially means as the number of trials approaches infinity. Okay, and then I just wrote my little statement that I mentioned before down just because that is important. Okay, so that's kind of connecting the empirical probability to theoretical probability. So that's what we're going to do next. So for theoretical probability, before we get into the actual definition, let's say when you roll a die and observe the number that's face up, the possible outcomes are going to be 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, 5, and 6. And if the die is a fair die, that means it's equally likely that you will roll any one of these 6 possible numbers. So we mentioned the term fair before with a fair coin, and that has to do with the phrase equally likely. So that kind of brings us to this definition, even though I mentioned it before. So if each outcome of an experiment has the same chance of occurring as any other outcome, we say that the outcomes are equally likely outcomes. Okay, so now that brings us to the definition of theoretical probability and how we're going to calculate it. So the theoretical probability of an event, which we read as the probability of event E, is going to be calculated using this formula. It's going to be the total number of outcomes favorable to E divided by the total number of possible outcomes. So it is super similar to how we calculated the empirical probability. It's just going to be a ratio, once again, just a fraction. Okay, so let's go ahead and take a look at some of these questions. So let's say that we roll a fair die, and if it's not mentioned, it's assumed to be a 6-sided die. So a fair die is rolled. We want it to determine the probability of the first one, rolling a 2. Okay, so I'm going to write this like this, the probability of rolling a 2, or you can once again do the probability of event E, where E is the event of rolling a 2. So the probability of rolling a 2 is going to be the number of times we can roll a 2 divided by the total number of possible outcomes. Okay, so the number of outcomes that result in a 2, that's just going to be a 2. The only way we can roll a 2 is just rolling a 2. So that's going to be one outcome divided by, it's a 6-sided die. So 6 possible outcomes, so just 1 out of 6. Okay, so let's take a look at the next one, the probability of rolling an even number. So the even numbers here are going to be 2, 4, and 6. So the probability of an even is going to be the number of times we can roll an even number divided by the total number of possible outcomes. there are 3 even numbers, so divide that by the total number of possible outcomes, and we get 3 over 6. Let's simplify that down to 1/2 or 0.5 if you want to write it as a decimal. Okay, next one, probability of rolling a number greater than 3. So greater than 3, that's going to be 4, 5, 6. So I'm going to write this as the probability greater than 3, or you can just once again write that as event E and do the probability of E. Probability greater than 3. There are 3 numbers greater than 3, so that's going to be 3 times out of the total number of outcomes, which is 6. So we get 1/2 once again. And for the next one, we have the probability of rolling a 7. So the probability of rolling a 7, we have to think about how many ways we can roll a 7. Well, we can't. If it's a 6-sided die, then it's going to be 0 options for rolling a 7. Divided by 6 total options, that's going to give us 0. Okay, and then for a number less than 7, so for a number less than 7, that's actually going to be every number on the die. It's going to be 1 through 6. So the probability of rolling a number less than 7 is going to be 6 possible outcomes divided by 6 total outcomes. 6 divided by 6 is 1. So once again, if you want to think about that as a percentage, that 1 represents 100% chance. Okay, so that brings us to some important probability facts. As we just saw, the probability of an event that cannot occur is going to be 0. And the probability of an event that must occur is 1. Every probability is going to be between 0 and 1 inclusive, and you can write it like that if you want. And something that's very important is the sum of all the probabilities of all possible outcomes of an experiment is going to equal 1. So if you add all of the probabilities, it's essentially saying that's 100% of your probabilities. Okay, let's do a couple more examples here. So the names of 9 birds and their food preferences are listed in this table below, right down here. And each of the 9 birds' names is listed on a slip of paper, and the 9 slips are placed in a bag. 1 slip is to be randomly selected from the bag. We want to determine the probability of the following. So for the first one, let's determine that the slip contains the name of a finch. Okay, so let's take a look at this table. So we have these types of birds. We want the probability that we pick out a finch, and it could be any type of finch, and it says that because I believe there are 2 of them. There is the goldfinch up top, and then there is the house finch down here. So that's going to be 2 possible finches out of 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 possible birds, so it's going to be 2 out of 9. Okay, and then for the next one, we want the probability the bird has a high attractiveness to cracked corn. So we have our 3 columns here on the right. We have peanut kernels, cracked corn, black-striped sunflower seeds, and then we have that bird's attractiveness to them. H is high attractiveness, M is medium attractiveness, L is low attractiveness. So we are looking at, which one are we looking at? Cracked corn. So we're looking at the second column. So we want the probability of randomly selecting one out that has a high attractiveness to cracked corn. There's only 1 bird that has an H there, so it's going to be 1 out of 9. Okay, now for the next one, we want a bird that has a low attractiveness to peanut kernels and a low attractiveness to cracked corn and a high attractiveness to black-striped sunflower seeds. Okay, so low attractiveness to peanut kernels. Peanut kernels is the first column, so I'm just going to highlight all of the L's here. And then we want a low attractiveness to cracked corn. So I'm going to highlight the L's in the cracked corn. And then we want a high attractiveness to black-striped sunflower seeds. So it looks like it's a lot. We're going to highlight all the H's for the black-striped sunflower seeds. So now we need to count how many satisfy all three of these conditions, and we're doing all three of these conditions because of the word and. Okay, so the ones that satisfy all three of these conditions are going to be the first one. It was low, low, high, and then it's going to be that evening grosbeak. And then the last one, it looks like the northern cardinal satisfies all of them as well. So that's going to be 3 total birds satisfy that. So that's going to be 3 out of 9 total. And just so I don't have to write out that whole thing, let's say that this is event E. So I'm just going to write it as the probability of event E is going to equal 3 out of 9. Which can be simplified to 1/3. Okay, and now for the last one here, we want the probability that a bird has a medium attractiveness to either peanut kernels or cracked corn or both. So the word "or" we have to remember is going to mean at least one. So let's take a look at medium attractiveness to peanut kernels. So peanut kernels, we have an M, M, and an M. And then we want medium for cracked corn. So M, that's an H, M, M, and M. And then we need to count them up. And since it's or, it can be either or. It does not have to be both this time. And is both, or is at least one. So that's going to be 1, 2, 3, 4, 5, and 6. So let's let this be event E once again. So it's going to be the probability of event E is there were 6 of them out of 9 total. That's going to simplify if we divide by a common factor of 3. Simplifies to 2/3. Okay, so for this last thing here, just one extra important probability fact. So in any experiment, an event must either occur or not occur. So what that actually means then is the sum of the probability that an event will occur plus the probability that it will not occur is going to equal 1. So writing that out is going to be the probability of A plus the probability of not A equals 1. And if you remember back to working with sets, you can think of that as kind of like the complement of A as not A. Okay, then what we can actually do here is we could solve for the probability of not A, and that's going to be equal to 1 minus the probability of A. So technically these are the same exact equations, just rearranged a little bit. So for example, if the probability that event A will occur is 5/12, then the probability that it will not occur is 1 minus 5/12, which you'd have to get common denominators, which would give us 7/12. And then similarly, if the probability that event A will not occur is 0.3, so notice that it's different, it's flipped this time, the probability that it will not occur is 0.3, then the probability that it will occur is just 1 minus 0.3, which is 0.7. So in this formula over on the right, you could reverse A and not A, rewriting it as the probability of A equals 1 minus the probability of not A, and it means the same exact thing. Okay, so let's do an example here. So let's say a standard deck of, we're using a standard deck of 52 playing cards. So here is the standard deck of 52 playing cards. We have our picture cards, which are also called face cards. So let me write that down. We have our number cards, which are 2 through 10, and then we have our aces. Okay, so this is going to be chopped up into 4 different suits. Each suit has an ace, 2 through 10, and the face cards. We have the hearts, clubs, diamonds, and spades. Each suit has 13 cards. And the red ones, the red cards are hearts and diamonds, as you can see. And then the black cards are clubs and spades. Okay, so let's do these questions. We have one card is going to be selected, at random from the deck of cards. Determine the probability that the card selected is, for the first one, is an 8. Okay, so this is going to be theoretical probability. It's going to be the number of ways we can choose an 8 divided by the total number of outcomes. Well, we know the total number of outcomes is 52 because there's 52 total cards. So now we have to determine how many 8s there are. There are 4 8s. There's one of each suit. So it's going to be 4 out of 52. We can simplify this. We can divide by 4 in the numerator and denominator and get 1 over 13. Okay, for the next one, the probability of not an 8, so the probability that it is not an 8 this time, we can go ahead and count up how many cards are not 8s, or we can just use what we just learned and say that's going to be 1 minus the probability that it is an 8, which is 1 minus 1 over 13, which is going to be 12 over 13. Okay, and just a reminder, for subtracting fractions, you would have to get common denominators. You would have to multiply 1. So you have to multiply this 1 by 13 over 13. So it becomes 13 over 13 minus 1 over 13. Subtract the numerators, we get 12 over 13. Okay, next one, the probability that it is a club. So we're going to have to count how many clubs there are, divide by the total number of cards. We know that there's 52 cards, and we also know that there are 13 clubs, so 13 out of 52, and we can actually reduce this. We can divide by 13 in the numerator and denominator and get 1/4, which should make sense because there's 4 suits. The clubs is just one of the 4 suits. Next one, we want the probability of a jack or queen or king. So the word or tells us how to do the problem. It means either or, so it means at least one. So essentially we're adding them up. So for jacks, kings, and queens, they are the face cards. There are 3 face cards from each suit. That means there's 12 of them total. So it helps when you have them right out in front of you. You can just count and get 12. So this is going to be 12 out of 52 total cards. And we can reduce that by a factor of 4, divide by 4 in the numerator and denominator. That'll give us 3 over 13. So if it says or, we just have to add them up. Not to get confused with the next one where it says and, the probability of a heart and a spade. So we need to go ahead and count how many are hearts and spades. So they need to be both a heart and a spade. A card cannot be a heart and a spade. Those are different suits. So this one's actually going to be 0. So the probability of a heart and a spade is 0 out of 52 cards, which is obviously just 0. Okay, and then for the next one, the last one here, probability that the card is greater than 5 and less than 9. So greater than 5 and less than 9, that's going to be 6, 7, 8. So we go ahead and count up how many are there. There are 12 of them there. So that's going to be 12 out of 52. Which once again simplifies to 3 out of 13. So I just let this be event E, and I just labeled it as the probability of event E. Okay, so that is it for this section.